Welcome everyone. Today I'm excited to present my master's thesis which focus on optimizing turbofan engine maintenance costs through accurate remaining useful prediction and explainable analysis. My name is Vincius James and I have completed the research as part of my master's in machine learning and artificial intelligence. Let's start by discussing the problem we are trying to solve and our approach to it. The goal is to enhance the maintenance process of turbofan engines, reduce cost, and improve safety by predicting their remaining useful life. We'll be utilizing advanced machine learning models to achieve this. The primary aim of this research is to design and implement predictive maintenance model through time series analysis and other models. We specifically focused on the precise estimation of the remaining useful life or RUL of industry equipment. This serves as the backbone of our research. Our objectives can be broken down into four main points. First, we aim to conduct a comprehensive literature review to understand the existing methodologies. Second, we will apply machine learning model to predict the remaining useful life. Third, we want to compare the performance of these models. And finally, we aim to make these models explainable for better interpretability. In our literature review, we delved into various machine learning models and their applications in predictive maintenance. We studied both traditional and deep learning algorithms and particularly focused on their effectiveness in predicting the remaining useful life of engines. We extended our literature review to also consider the achievements in hybrid models and explainability. We noticed a gap in real world implementation studies, which our research aims to fill. This gives us a strong starting point and context for our work. Here we came across multiple papers which delves into the machine learning and deep learning models that are commonly used for predicting the remaining useful life or RUL of machinery. This part of literature review where we have explored various approaches to solve this problem. This is the introduction to the kind of models we'll be discussing. First, linear regression, then the time series analysis, then the random forest, and MLP and LSTM, and we'll see XGBoost and ANN. These are all the models which used in many papers. After reviewing all the papers, we decided to have a study to understand which model works well and what technology needs to be used for better results. We extended our literature review to also consider the advancements in hybrid models and explainability. We noticed a gap in real-world implementation studies which our research aims to fill. This gives us a strong starting point and context for our work. We explored some of the most innovative approaches and notable gaps in the realm of predicting remaining useful life. First, we have attention-based deep learning, a groundbreaking method that uses by LSTM with attention mechanisms. This is not only enhance the prediction accuracy but also captures long-term dependencies in features. Next is the joint encoder regression model, the unique architecture with the auto encoding with regression, streamlining the RUL estimation process. We also looked at convolutional ConNet-based TNN, which solely uses the convolutional neural network. This result in a more efficient and compact model suitable for real-time applications. And then we have hybrid models which leverage both LSTMs and CNNs, offering a harmonious blend of feature extraction and sequence modeling for superior RUL predictions. Finally, we touch upon existing research gaps. The literature so far emphasizes the promise of hybrid models, but also points out the challenges like the need for better model, the explainability, real-world applications, and the data set specific optimizations. All these areas are ripe for future research. Our research methodology is systematic and multifaceted. It starts with understanding the business context of the predictive maintenance, followed by diving into the details of the CMAPS dataset. We then move on to the model building, tuning, and evaluation. In this continuation of our literature review, we focus on the key insights from various studies. We have explored attention-based deep learning models, joint encoder regression architecture, and conv-based deep neural network as mentioned in the previous slide. We also discussed hybrid models that combine LSTM and CNN for superior ROL estimation. The research gaps identified include the need for model explainability, real-world implementation studies, and the dataset specific optimizations. In the research methodology section, our next focus is the datasets that we use for the study. We utilize the CMAPS dataset, which stands for Commercial Modular Aero Propulsion System Simulation. This dataset is a standard benchmark for predictive maintenance tasks in the aviation industry. The CMAPS database comprises 4 sub-datasets FD001, 002, 003 and 004. Each of these offers a unique combination of operational conditions and fault scenarios, thereby enabling a comprehensive evaluation of the predictive maintenance algorithms. So, why use multiple datasets? Well, it is about versatility, generalization, benchmarking, and real-world applicability. These datasets allow us to test our algorithms in varying complexities under different conditions. This ensures that the models we build are not just theoretically sound but practically applicable. Lastly, it is worth mentioning that the iterative modeling from FD001 to 004 enhances the robustness, adaptability, and reliability of the algorithms we develop. The iterative approach prepares our models for the real-world scenarios where the engines operate under different conditions and have various fault tolerances. Moving on to the specifics of the CMAPS dataset, let's discuss what each one brings to the table. Starting with FD001, this dataset contains just one operating condition and is focused on capturing sensor readings and faults under the singular condition. It is ideal for basic predictive maintenance scenarios where the environment is stable. Next, we have FD002. FD002 comes with 6 different operating conditions, adding a layer of complexity. It captures the variability in sensor readings and fault development, making it well suited for models that need to adapt to different operating environments. Now, FD003 takes a bit of different approach. While it also contains one operating condition, much like FD001, its focus is on capturing faults that are not related to the operating conditions. This makes it especially useful for studying the inherent reliability of the system. And last but not the least, we have FD004, which is essentially a blend of FD002 and FD003, which captures data under 6 operating conditions and consider multiple types of fault, making it representative of complex real-world scenarios. So in summary, each dataset serves a specific purpose and complexity level, allowing us to progressively test and fine-tune our predictive maintenance models. As we transition into the research methodology section of this presentation, let's dive into the key steps involved in handling and analyzing our dataset. We start off with the data loading, where we have three primary datasets: training, testing, and the RUL dataset. This forms the backbone of our research. Next, we move to the feature engineering. Here, we meticulously exclude uniformity features and introduce lagged variables to capture the history of sensor readings. This is a crucial step for enhancing the predictive power of our models. Then comes the explorative data analysis. Through a series of visualizations, statistical summaries, and correlation studies, we get a deeper understanding of our data. It helps in us unearth hidden patterns and anomalies that could impact our predictive models. Now let's talk about the data pre-processing. First, we compute the remaining useful life by reverse counting the cycles per engine. Additionally, we apply the augmented decay-fuller test or ADF test to ensure that the stationarity of our time series data. If the series is not stationary, we apply differencing to make it stationary. In the realm of data transformation, we have lag variables to embed the historical context into the data. We also apply the Z-score normalization for feature scaling. Again, differencing is used to make the series stationary, capturing the differences in sensors reading over time. Lastly, we employ survival analysis techniques like Kaplan-Meier estimator and the Cox proportional hazards model to estimate the survival function and assess the impact of various factors on survival time. In summary, each of these steps is meticulously designed and executed to build a robust and reliable predictive maintenance model. As we transition from the research methodology to the analysis, let's focus on how we dissected the NASA CMAPS datasets to predict the remaining useful life of turbofan engines, a critical component in the aviation industry. The first step was exploratory data analysis, or the EDA. We loaded the data and carried out the basic examination to get a grasp of its structure and the characteristic. We paid particular attention to the count of engines, the number of cycles they underwent, and how these cycles are distributed across different engines. Visualization helps us understand the degradation of sensors over time, which is crucial for predicting the remaining useful life. Speaking of remaining useful life, we calculated it by subtracting the current cycle from the total cycles for each engine. This was our target variable for predictive modeling. Then we moved on with building a baseline model using the linear regression. We choose sensors 2, S4 and S11 as our predictors. The model's performance was gauged using the RMSE metric on the test set, giving us the baseline to compare with more complex models. Lastly, we employed various visual techniques to augment our understanding. We used histograms to visualize the distribution of engine cycles, lines plots to show sensor regradation over time, and the scalar plots to compare the true RUL versus the predicted RUL from our baseline model. In the essence, this comprehensive analysis sets the stage for us to dive deeper into more advanced modeling techniques, thereby bringing us closer to our objective of effective predictive maintenance. Continuing from our baseline linear regression model, we ventured into the more advanced methodology, started with SVR, support vector regression. We used readings from various sensors as predicted, aiming for a more flexible model that could capture complex relationships. The performance of the SPR model was measured using the RMSE, which provided a quantitative assessment of the model's accuracy. Next, we explored the time series analysis, specifically using the ARIMA model. Given the sequential nature of our data, it is crucial to capture the underlying temporal patterns, and ARIMA allows us to just do that. To fine-tune our model, we use the AIC to determine the optimal number of lags. We also visualize different time series behavior to emphasize the importance of stationarity in our data. Lastly, we employed survival analysis techniques. The Kaplan-Meier estimator was used to estimate the survival function, essentially telling us the probability that an engine would survive past a certain point in time. To further understand which factors influence entire lifespan, we used the Cox proportional hazards model. We even conducted a deep dive into the behavior of a specific sensor, that is S7, to check for stationarity, enhancing the robustness for our predictive models. In summary, each of these methodologies offer a unique lens to view our dataset, enriching our analysis and bringing us closer to achieving effective predictive maintenance. In our quest for a more robust model, we utilized random forest, an ensemble method that leverages multiple decision trees. One of the most valuable aspects of random forest is its ability to rank features based on their importance. In our case, this ranking revealed that sensors play a pivotal role in predicting the remaining useful life. Our random forest model was evaluated on the test set and achieved an impressive RMSE, which signifies its predictive accuracy. Lagged multi-layer perceptron (MLP). Moving further into the neural network, we explored that the lagged multi-layer perceptron, or MLP. This model is particularly designed to capture non-linear relationship in the data. We introduced lagged features to account for the sequential nature of our data. The model underwent condition-based standardization and was fine-tuned to achieve optimal performance. We monitored the training dynamics closely to evaluate the model's performance using various metrics and visual evaluation. evaluations. As we wrap our analysis, it's crucial to note that we adopted a multifaceted approach to gain a comprehensive understanding of a data set, from the basic linear regression to the advanced neural network like the MLP. Each model provides unique insight into the problem of predictive maintenance. The combined result of this diverse model contribute to formulating an optimal predictive maintenance strategy for the turbofan engines. As we delve into the concept of survival analysis, one of the key techniques we employed is the plan merit estimator. The curve you see on the screen showcases the probability of an engine survival. On the other hand, continuing to operate as the operation cycles progress. This survival curve is a powerful tool offering actionable insights into when we might expect an engine to fail, thereby enabling more effective maintenance scheduling. It gives us an empirical understanding of the engine's reliability over time, enriching our predictive maintenance toolkit. In the context of our survival analysis, we also calculated the hazard ratios for different predictors. The hazard ratio is a crucial metric that helps us to understand the risk associated with each variable or the predictor in the model. A hazard ratio greater than 1 indicates an increased risk of an engine failure associated with that specific predictor. Conversely, a hazard ratio less than 1 suggests that the predictor has a protective effect, reducing the risk of failure. By quantifying these ratios, we gain an analytical edge in identifying the most influential factors that affecting the engine reliability. As we proceed further into the results, let's discuss the heart of our project: model building and evaluation result. We start with model selection, then we explore the range of algorithms from basic linear regressions to the neural network. This idea to understand which model resonates better with our data sets unique characteristics. Then we optimize these models through model tuning. We employ techniques like grid search to fine tune hyperparameters, ensures that models are not just fit but finely tuned to our specific problem. Next is the model evaluation, where we measure the efficacy of our models using the well-established metrics like the RMSE or the R square value. This helps to quantify how well our models are performing. Now let's delve into the models that we explored. Linear regression serves as our baseline model with an RMSE close to 20.85 on the test set. For the time series analysis, we use the AIC metrics to determine the optimal number of lags. SVM regression showed a notable 35.7% improvement over our baseline model. Random forest was optimized for performance, showing commendable result after tuning. LSTM achieved an RMSE of 14.5 and R square of 0.88 on the test set, indicating high predictive accuracy. Lagged MLP also shows a promising result with the 14.3 on the test set RMSE and R2 square of 0.93. In the summary, each model offered unique insights and varying levels of predictive power, which bring us closer to the determined most effective predictive maintenance strategy for the turbofan engines. In our time series analysis, two critical statistical tools we employ are the autocorrelation function ACF and the partial autocorrelation function PACF. These functions help us understand the correlation structure in our time series data. ACF gives us the correlation between the current observation and previous observation, while PACF provides the pure correlation of an observation with its lag, removing the effect of other intervening observations. These tools are especially useful for identifying the model parameters for ARIMA, a popular time series forecasting model. By optimizing these parameters, we can significantly improve our model's ability to predict the RUL of an engine. And in the predictive modeling task, examining the residuals of the references between the observed and the predicted values is the crucial step for the model validation. In the study, we have included a density plot in the residuals to dig deeper into this aspect. These plot help us understand whether the errors in our models are normally distributed, which is an underlying assumption in many statistical models. If the density plots resembles a normal distribution, it is an indication that our model is well fitted to the data. Conversely, any skewness or heavy tails, the plot might significantly signify that there might be room for further improvements in the predictive algorithm. This is the result we obtained so far. If we check RMSE for the linear regression, it is 29.66, and for SVR it is 20.54, and for ARIMA it is 20.54, and survival analysis it is 26.58, and random forest it is 17.88, and lagged MLP it is 10.7, and lagged NLP it is better. And when it comes to the R2, linear regression it is 0.65, support vector regression it is 0.75, and survival analysis it is 0.7, and random forest is 0.81, and lagged MLP is 0.93. So for the R2, even lagged NLP works better. Today we have seen more how machine learning can help in predicting engine failure, saving both time and money in the aviation industry. Our models are accurate, but there are more work to do. We need to make them easier to understand the test in the real world situations. Thanks for your attention, and I'm excited to see where this research will go next. These are the few main references which I used, and I built my paper on top of that. Thank you. Thank you.